Thank you very much for the invitation. So my talk will be about machine learning for mechanism design, and more specifically about sample complexity of data-driven mechanism design for pricing and auctions. Okay, and oops, let me see. Okay, and broadly speaking, by data-driven mechanism design, I mean the use of machine learning to design and analyze mechanisms based on data. Now, this idea itself was proposed a couple of decades ago, and I had one of the early works in this direction. But really, in recent years, there has been a surge of interest in this direction, with a lot of interesting contributions on this topic by many different people. And this interest is actually quite natural, because this data-driven approach can actually help us overcome challenges faced by traditional manual approaches to mechanism design. Okay, and in particular, in many interesting cases, including some of the cases I'll talk about today, it is hopeless, at least according to our current machinery, it is hopeless to analytically or by hand, it's hopeless to derive analytically or by hand the optimal or the nearly optimal mechanism, but we can hope to instead use machine learning and data and to learn the mechanism from a restricted class of mechanisms that is good for our specific type of data distribution. Okay, and in my talk in particular, I will focus on statistical or sample complexity guarantees for data-driven mechanism design for revenue maximization for multi-item scenario. And at a high level, the main result of this work is a general unified simple analysis for mechanism design classes whose revenue is a sufficiently structured function in a sense that I will describe during my talk. Okay, and a lot of what I'll talk about today is joint work with Alan Petersic and Thomas Sandholm. It appeared in EC 2018, but I'll also mention at the end an even more general result that we had recently in STOCK 2021. Okay, so this is a high-level introduction. Now we can dive into details. Throughout my talk, I'll be talking about mechanism design for sales settings. So here we'll have a set of M items and N buyers, and and of course each buyer I will have a value VI of B for each bundle of the items for sale. And I'll denote by VI the vector or buyer's values for all bundles, for all subsets of the items. Okay, and we'll be talking about mechanisms for revenue maximizations, and these can either be auctions or pricing mechanisms. And at the high level, as we know, mechanism determines which buyers receive which items and what they pay. Okay, and more specifically, a mechanism will be defined by an allocation function and by a payment function. And the allocation function defines which buyers receive which items, and the payment function defines how much each buyer pays. And then the revenue of our mechanism will be just the sum of the payments. Okay, just as an example, as a quick example, we could think about posted price mechanisms, where the seller is trying to sell a number of items, and then what he does, he just puts a price per item. And then the buyers come in some fixed but arbitrary order, and then they buy the items that maximize their utility. Or as another quick example, we could have a second price auction with a reserve, right? So here the auctioneer will set the reserve price R, then bidders would submit bids, and then the highest bidder would wins, and if its bid is at least R, and then he pays the maximum of the second highest bid and of the reserve price. So in this quick example here, where I have 4 bidders and these are their bids, then if we set the reserve price to be 8, then our revenue will be 8 because the highest bidder wins and pays the reserve price. On the other hand, if we set the reserve price to be 6, the higher bidder still wins and the reserve and he pays the second highest bid. Okay, so our revenue will be 7. So these are just quick examples of mechanisms to keep in mind throughout the talk. But as I mentioned, our focus here is on data-driven mechanism design. And let me describe what do I mean by this. Okay, here is statistical or distributional learning formalization of this. Okay, so what we're gonna do, we're gonna first fix a problem that we want to solve. And this can be just the problem of pricing one or more items that we have for sale. So we fix the problem that we want to solve. And then what we do, we also fix a large parameterized family of mechanisms for our problem. And this can either be a family of mechanisms that is commonly used in practice, or maybe a family of mechanisms for which you have analytical reasons to believe it is good for our specific setting. Okay, and then what we do, we take a set of bias values from the underlying distribution. And then we use this set of typical samples of bias values for various subsets of the item. So use this set of typical samples in order that we are assuming technically that they come IID from some fixed unknown distribution over, or fixed unknown or known distribution over bias values, right? And we use this set of typical samples in order to find the mechanism from our fixed parameterized family of mechanisms. And we hope to prove that this mechanism that we find based on this set of typical bias values, we want this mechanism to do well on new random valuation vectors coming from the same distribution as a training set. Okay, and let me say this again more slowly. So we fix a problem that we want to solve, and this can be an auction problem or a pricing problem. Okay, and then what we do, we also fix a large parameterized family of mechanisms for our problem. Okay, so for example, if we are considering a single item auction, our family of mechanisms, our parameterized family of mechanisms could be the set of second price auctions with a reserve. Okay, or if we are trying to price multiple items for sale, then our set of parameterized mechanisms could be the set of all posted item pricings. Okay, and then what we do, we take a set of bias values from an underlying distribution. Okay, and so in particular, each sample in our set will tell us what is the value for each of the buyers for each subset of the items for sale. And we assume that these samples are, of course, drawn IID from this distribution. Okay, so for example, for the case of second price auctions with reserve prices, we have only one item for sale. So when each sample will simply list for each buyer what is the value of the buyer for the given item, right? And this will be how sample one will going to look like. And then we have capital N such samples. Okay, or if we are doing, or for the case for posted price mechanisms, so we are trying to price multiple items for sale, then each sample will just list for the value of each buyer for the various subsets of the items. So this is an example of a sample. This will be sample one. It lists for buyer one its value for all subsets of the items, and we'll do the same for all the buyers, right? And this is how a sample will look like, and we have capital N such samples. This is capital N is a sample size. Okay, so basically we take a sample from of bias values from a fixed distribution of our bias values, and we want to use a set of typical samples in order to find the mechanism that has high expected revenue on new random valuation vectors. And in particular, we want this mechanism that we find to compete with the best mechanism from our fixed family of mechanisms with respect to the underlying distribution of our bias values. Okay, so this is really just a natural kind of statistical learning or distributional learning formalization of mechanism design as a learning problem. And a very, very natural approach commonly using machine learning is just to solve this problem is just to find the mechanism M hat that is nearly optimal over the set of typical samples. Yeah, so this of course makes a lot of sense, right? All we have is the samples. So makes sense to find a mechanism that is nearly optimal over the given set of samples, of typical samples. But of course, a key question is whether this mechanism M hat that does all over the set of typical samples will actually generalize. Will it have high expected revenue on new random valuation vectors that come from the same distribution as a training set of typical instances? And in particular, will it compete with the best mechanism from our family of mechanisms? Okay, so this is a key, right? So for example, just to be even more concrete, for the case of second price auctions of a reserve, and of course, the mechanism M hat that we find based on the training set of typical samples will of course do well on this training set of typical samples, but the key question is whether it will do well on new random valuation vectors that we have not seen in the training set. So in other words, will it generalize? Okay, so this is a key sample complexity question. We call it in machine learning theory a sample complexity question. And so now, of course, the answer to this question, whether this mechanism M hat will generalize or not on instances beyond those that we have seen in the training set. So the answer to this question will depend on how many typical instances we have seen in the training set. Okay, and so this brings up a key question, a key sample complexity question. How large should our set of typical instances be in order to guarantee that the mechanism that does well over the training set of typical instances will also do well on new random instances? Okay, and one learning theory tools that we use, that has been used and that we have used in our work to address this question is what we call uniform convergence bounds. Okay, and what are these uniform convergence bounds? They are bounds on the number of samples we need to see in the training set so that we can guarantee that with high probability over the draw of the training set of typical instances, we have it uniformly for all mechanisms in our set of mechanisms. We have it their average revenue over the training set of typical instances is close, say additively epsilon close to their expected revenue. Okay, and these uniform convergence bounds are very, very nice. They're very strong, they're very nice. And why very nice? Because once we have enough samples in the training set to guarantee uniform convergence, then we will know that a mechanism M hat that does all over the training set of typical instances will also generalize. And in particular, its revenue will be close to the revenue of the best mechanism in our fixed parameterized family of mechanisms on new random instances. So once we have enough samples to achieve uniform convergence, we basically get a generalization. And we also know from learning theory that the number of samples that we need to achieve uniform convergence will depend on the intrinsic complexity of or the intrinsic dimension of the family of mechanisms that we are looking at, the intrinsic complexity of this family of mechanisms, calligraphic M. And we know that, and then this notion of dimension is then a key quantity in a sample complexity bounds of the form that I have here on this slide, right? Which basically tell us how many samples we need to achieve uniform convergence, and thus really generalization to do well on new random instances. Okay, and in case you've not seen it at a very high level, what is this notion of dimension, of intrinsic notion of dimension at a very, very high level? It captures the ability of the revenue functions in our family of induced by mechanisms in our family. Okay, so it captures the ability of these revenue functions to fit complex patterns. Because the more complex patterns you can fit, the more samples you need to generalize and not overfit. Okay, so that's a very high level. And also at a very high level, the challenge when you are trying to analyze the intrinsic complexity of these mechanisms is that, they're often more complex. The induced revenue functions are often much more challenging than what we typically see in learning theory. They have many discontinuities, and this really stems from the fact that these mechanisms, sometimes they have complex objects with combinatorial modules and interesting interdependencies between the modules. Okay, so there is a challenge that we have to overcome, and the great news is that in our work, we are able to overcome this challenge, and we are able to extend tools from learning theory in order to provide a general tool for analyzing the intrinsic complexity or the intrinsic dimension for mechanism classes whose revenue function is a piecewise structure function of the class's parameter. Okay, and I'll define, again, I'll go through this in more details in a bit, but before going to the details, I want to mention that this resolvent has many applications to many multi-item, multi-buyer mechanism design scenarios, including second price auctions with reserves, posted price mechanisms, two-part tariffs, parameterized ECG auctions, and so on. Okay, so this is the main result at a high level. Now to describe this result a bit in more detail, I need to give you a very quick, a very brief two-slide overview what this notion of dimension really is, what this learning theoretic notion of dimension is. Okay, and so if we are studying the sample complexity of, or the dimension of classes of functions that are simpler, like binary functions, Right? So think about, for example, linear separators in RV, or you just pick a hyperplane and everything below the hyperplane is labeled minus, and everything about the hyperplane is labeled plus. Right? So if we're thinking about the complexity or the sample complexity of simpler binary valued functions, then we typically use a notion of VC dimension. Okay, so Vapnik-Chervonenkis dimension. And what is the VC dimension of a class of binary valued functions? Is just the cardinality of the largest set S of that can be labeled in all possible ways, in all possible 2 to the size of S ways by functions in our function class H. Right, and in the case where I can actually label a set S in all possible ways by functions in my function class H, I say that the set S is shattered by functions in my function class H. And so really the VC dimension is just the cardinality of the larger set S that can be shattered by functions in my function class H. Okay, so just as a quick example, if we're thinking about linear separators in R2, right, then you can easily show that the VC dimension of this set of linear separators is 3. Why? Because we can show that there exists a set of 3 points, like these 3 points here, that can be labeled in all possible 8 ways by linear separators. You can achieve all binary labelings on this set by using linear separators. But you can also show that no set of 4 points in R2 can be labeled in all 16 ways by linear separators. Okay, this is just a quick example, but going back to our mechanism design setting, we know that we're trying to analyze the sample complexity of real valued function classes, right? The revenue functions induced by our mechanisms. So we need to consider the notion of complexity for real valued function classes. And the one that we consider in our work is what we call pseudo dimension, which really is just a very natural extension of the VC dimension to real valued function classes. Okay, so what is the pseudo dimension of a function class F? Is just the cardinality of the largest set S that can now be shattered in a real valued sense by function in my function class F. Okay, so more slowly, what is the pseudo dimension of a function class F? It's just the cardinality of the largest set S of n points, now along with some thresholds y1, y2, yn, such that all 2 to the n above and below patterns can be achieved by functions in my function class on this set of n points. Okay, so here's a quick example on n equals 2. There should exist a function f1 in my function class that achieves the below pattern on my 2 points, x1 and x2. So we should have f1 of x1 is smaller than y1, f1 of x2 should be smaller than y2. There should exist a function f2 in my function class that achieves the above-below pattern. That means f2 of x1 is greater than y1 and f2 of x2 is smaller than y2. And there should also exist a function f3 that achieves the below-above pattern, and finally a function f4 that achieves the above-above pattern. Okay, and if you really think about it, the pseudo dimension of a function class F is just the VC dimension of a relative binary set of functions. But really, for now work and in my talk today, this is kind of the basic definition is the one that we're going to use. Okay, now with this brief overview to what pseudo dimension is, so it's just the combinatorial notion of quantity quantifying the intrinsic complexity from a learning point of view of a function class. Now, this quick introduction, I'm now ready to kind of state more formally our results for mechanism design. Okay, and I'll start by mentioning a simple proof or simple analysis for the class of second price auctions with reserves. And this then motivates a much more general result applicable more broadly. Okay, so let's recall, I talked about it at the beginning, but just let's recall what is a second price auction with a reserve. Well, we're in a single item case, we have multi-bidder scenario. The auctioneer sets a reserve price R, and then the bidder submit bids, and the highest bidder wins if its bid is a list R, and pays the maximum of the second highest bid and the reserve price R. So in this case, we really have just one parameter. So our mechanism class is parameterized just by one parameter, the reserve price. And for this case, we can then show that the pseudo dimension of our family of mechanisms is a constant. In particular, is at most 2. Okay, and I want to mention at a high level the main ideas behind the proof. So the key idea is, the first key observation is a key structure resolver says that if we fix a set of bids and then we vary the reserve price, we can observe that the revenue function is just a piecewise linear function of the reserve. It looks like this here. And this is simply because when the reserve price is smaller than the second highest bid, then the revenue is the second highest bid. When the reserve price is in between the second highest bid and the highest bid, then the revenue we get is the reserve price. So I get this piece here, right? And when the reserve price is bigger than the highest bid, then nobody gets anything, and so nobody pays anything. So the revenue goes to zero. Okay. Now using this observation, this structure result, then we can then show that if we have a set of n samples, so not only just a fixed set of bits, not only just one sample, but now we have n samples, we can kind of count the number of binary patterns induced on the set of endpoints, right? Because this is what we need to be able to analyze the pseudo dimension, how many labelings, how many patterns, above below patterns you can achieve on endpoints. And you can show it's only linear. And then this will be then a key fact to then argue that the pseudo dimension is constant. And how do we show it's linear? And this will becoming a little bit more technical, just for a minute. So how do we show it's linear, the number of patterns you can achieve on endpoints? Well, all you have to observe is that if we fix a set of bits, say the ith sample in our training set, and if we also fix a revenue threshold, which is what we need to do when we think about pseudo dimension, then we can observe that as we scan the reserve price from 0 to infinity, basically there will be two cutoff values, these critical values that I marked here, where kind of the revenue goes from being below this revenue threshold to above this revenue threshold in this segment, again to below this revenue threshold. So we really have kind of two critical values if we have just one sample. But now if we have n samples, now we have 2 times n cutoff values, and then this can be used to argue that we basically on n samples, we can achieve at most 2n plus 1 above below patterns. Okay, and now all we have to do is to recall that the pseudo dimension, or this intrinsic measure of complexity, is just the cardinality of the largest set of n points on which an exponential number of patterns, 2 to the n binary patterns, are achievable. So that means to compute the pseudo dimension, all we have to do is to compute the largest value of n, on which on one hand an exponential number of patterns is achievable, but on the other hand, we know from the structure of our mechanism design class that only a linear number of patterns is achievable on them. So we just have to solve for the largest value of n for which this inequality here is satisfied, and so you get that the pseudo dimension is a constant. Okay, so I want to mention, so this is brief, quick, but hopefully I convey the main ideas. Now I want to mention that this result itself was proven in earlier work by Tim Ravgarden and Jane Morgenstern, and even earlier by Mehri Arnoeri on Andres Medina. But the interesting fact of our proof is much simpler, and it motivates a much more general result applicable more broadly. Okay, so what is this more general result? So now it will apply to mechanism design classes that are high dimensional and that satisfy what we call DT delineability. Okay, what do I mean by this? So there are two conditions. So first, our mechanism design class will now be parameterized not only by one parameter, but by the real valued parameters. Second, we're going to assume that if we fix a set of bias values and we vary the parameters, we can partition the parameter space with at most t hyperplanes, such that in each cell induced by that partition, the revenue function is linear. Right? So for example, in the second price auction of reserve prices, D was 1 and T was 2, because my function was piecewise linear with 3 pieces. But in general, this can be, I could have D equals 2, and maybe have 2 parameters, and maybe T, the number of hyperplanes, is 5. And in general, it can be any D and any T. So basically, what we can show that if our mechanism design class is DT delineable, meaning really it's parameterized by vectors in RD, and if we fix a set of bias values, our revenue function is piecewise linear with a number of pieces given by at most T hyperplanes, then we can compute that the pseudo dimension of our parameter of our mechanism class is up to constant factors D log dt. And this is really a great bound because D is the number of parameters, and so we're only linear in the number of parameters, and moreover, we're only logarithmic in T, which typically is higher quantity. Okay, and I'm not going to go through the proof. The proof will be similar to what I showed you for second price auction reserve. Of course, we use more complex machinery because it's in high dimensions. But all we do is on a set of n samples, you can count the number of patterns. You can binary patterns. You can above below patterns. You can induce functions from a mechanism design class. And so I'm happy to talk about the proof of line. But what I want to do for the rest of the talk, I want to give you more examples of where this theorem applies beyond the second price auctions reserve. Okay, and let me And one first example here is the class that we've seen at the beginning of the talk, posted price mechanisms. Right, so here we have a multi-item, multi-buyer scenario, right? And the seller, what the seller does, sets a fixed price per item, and then the buyers come in a fixed but arbitrary order, and they buy what they want at the current prices. Okay, and we can show by using our general theorem that the two-dimension of this family of mechanism, which then is up to log factors the number of items squared. Okay, and how do we show that? Well, we're just gonna, what we have to argue is that it's DT, we need to understand we need to argue that it's DT delineable, right? Where D is the number of items, the number of parameters, which is the number of items, and we have to compute what T is. In this case, it will be the number of bidders times 2 to the number of items choose 2. Okay, and since I do have, it looks like I do have time, I'm just gonna, I mean, this will be super quick, the proof, just to get an idea of how do you reason. I want to go briefly through it, even if it's quick. Just to give you a feel about how the proof goes. So we want to show that the class of positive price mechanisms is DT delineable, where D is the number of items and T is this quantity here. Now, of course, D stands for the number of parameters, and of course, for positive prices, we set the price per item, so it's obvious that the number of parameters is the number of items. Now let's see why T is this quantity that I have here, right? So what is T? T is the number of hyperplanes that we need in order to partition the parameter space such that in each set induced by the partition, the revenue function is linear, by definition of DT delineability. Okay, and how do we show that? Well, we just first observe that for every buyer and for every pair of bundles, the decision boundary where the buyer prefers one bundle over the other is a hyperplane. Okay. Then we use
3 minutes.
Yes, thank you. Then we use the fact that the number of bundles is just 2 to the number of items. And so this then implies that there are at most number of buyers times 2 to the number of items just to hyperplanes, such that in any region induced by these hyperplanes, for any two prices in that region, really the buyer, any buyer, all the buyers have the same, any buyer has the same preference ordering over the bundles. Okay, and then the final observation is just that on all the buyers' preference orderings over all bundles are fixed, when the bundles that they end up buying are fixed. And so when you think about it, then this implies that the revenue function is a linear function of the price of the items that they buy. Okay, so you can basically, it's not too hard. That's what I'm trying to point out here. Actually, it's not really hard at all to prove that the class of positive price mechanisms is delineable with these parameters, which then imply a bound on the pseudo-dimension and then a bound on sample complexity. Okay, and very similar arguments we can do for many other classes. So let me mention one more, which is a class of two-part tariffs. So for here we have a single item and we have a multi-buyer scenario. We all have multiple units of the item. If you want, you can think about having an unrestricted number of copies of the items. And we assume that each buyer wants to buy the most kappa units. Okay, and then the way the pricing mechanism goes, the seller sets up an upfront fee P0, and then an additional fee P1 for any additional unit. So if a buyer wants to buy K units, then he has to pay P0 plus K times P1. And of course, each buyer is going to buy the number of units, maximizing each utility. Okay, and then we can also, of course, consider a menu of L two-part tariffs. And in this case, the buyer will choose both a tariff and a number of units to buy to maximize his utility. Okay, and the interesting part is basically we can again prove a bound of the pseudo-dimension of this family of pricing mechanisms, and we show it's up to log factors L, upward bounded by L. And the way you prove it is just showing it is the class is delineable with the relevant parameters. And again, the proof is quite simple. It just follows a similar pattern that I showed you for positive price mechanisms, so not very hard. Okay, and in our work, actually, we show we analyze the pseudo-dimension. We show that our general theorem can be applied to analyze the pseudo-dimension of other mechanism classes beyond the ones that I mentioned, like parameterized VCG auctions, like Athens maximizer auctions, and some other simple cases of lotteries. Okay, and actually, I want to mention that in all of these cases, actually, we are able to apply this DT delineability result that I mentioned, so the general theorem that I mentioned so far, right? What I assume is that if I fix a set of buyers' values and vary the parameters, the revenue function is piecewise linear with an appropriate number of pieces, right? And so we're able to analyze all of these mechanism classes using just that DT delineability result. Okay, but what if you are now, you like my talk and you are trying to apply this result to your favorite mechanism design problem or to your favorite economic, data-driven economic problem? What if your performance function is not piecewise linear anymore?
Nina, could you wrap up, please?
Yes, in a second. Yeah, what if your performance function is not piecewise linear anymore? The good news, you have a new result that says that if it's piecewise structured, then you can still get a sample complexity bound. Okay, and I leave it at that. And just to summarize, so in this work, we basically give a general way to analyze the intrinsic complexity of parameterized family of mechanisms whose revenue function is piecewise structured. This then implies bounds on sample complexity for data-driven mechanism design. In our work, we focused on the case of mostly on the case of revenue maximization, and it would be very interesting and for selling mechanisms, and it would be interesting to use this machinery to understand data-driven mechanism design beyond selling, and yeah, and more generally to apply this technology for data-driven for other economic problems.